Hello everyone, welcome to the first virtual problem analysis set brought to you by the social distancing we're all meant to be doing. So hopefully this will be useful. We don't have the advantage of doing this in person and you guys being able to ask questions. However, I think there's some advantage to this being a video because you're able to go through it at your own pace and rewatch it as much as you'd like. So the problem we're going to start out with is the Brayton cycle with regeneration. And this is a variation of a normal Brayton cycle. And so what we're going to do here is we're going to cover some initial background theory, and then we're going to get into the question. So the place to start is the standard Brayton cycle. The standard Brayton cycle is a power cycle, just like the Rankine cycle. However, rather than using water as the working fluid, this one uses air. So air enters the compressor. It gets compressed, and at this point it's going to be high pressure, and likely, or it will be hotter than at state 1. Then it goes through the compressor and heat addition is added. In reality, this heat addition would be through adding fuel, but we model it as heat addition, as when the fuel combusts, there is heat added. Then at point 3, it's going to be high pressure, high heat, and we're going to extract that heat through the turbine. So a couple of things to notice here. You'll notice that the compressor and the turbine are attached with a shaft, and power or net power is drawn out. In reality, when we analyze it, we're going to be analyzing each section. So we're going to be interested in power input to the compressor and power output of the turbine, though in the real application these are connected, which is why it's drawn this way as a schematic. So to relate this to the real world, this is a gas turbine engine. One application that many of you would have seen is an aircraft engine uses this type of engine. And with most aircraft engines, you'd be flying with a turbofan engine, which is that large fan with the spiral design on the end that you see at the front of an airplane. And with these, a lot of the thrust actually comes from the spinning of that fan, not from the air passing through the turbine. And so there's this large bypass section. But the insides of the turbine are what we modeled with the Brayton cycle. So we have a compressor, a combustor. This is where the heat, aka the fluid, is added, and then the turbine is where all the power comes from, and connecting the turbine and the compressor is a shaft. So again, that's why we model it that way here. So the key concepts we need to solve these types of cycles are, of course, first law. We've been using this since the beginning of the course. This is the slightly simplified version of first law, where we are assuming steady state. And one inlet, one outlet. And the inlet we're calling state 1, and the outlet we're calling state 2. And this is why we have H1 minus H2. So you'll have worked with this quite a bit already. The next thing we need to understand is this idea of isentropic processes. So if a process is fully reversible and adiabatic, then we know S1 is equal to S2, and this can be easily proven from second law. And we did that in the past tutorial. So there's this extra tool that we have for air, which is very nice and easy to use, and this is just a direct result of this. So don't worry too much about understanding exactly what the pressure reduced means. We're going to use it very practically, and with a couple times of using it, you'll understand where this comes, or how to use this at least. And this PRs you can find on table A22 in your textbook. The next thing is isentropic efficiency. So we have one equation for a turbine and one for a compressor. Now, by definition, our compressor efficiency is equal to the power that we're actually producing versus the isentropic power. Another way of saying that is this is the ideal or best case scenario power we can produce. This one is can't always be used in every case, and so I'll show you just right now how that works. So if you have a turbine, you have air coming through the inlet and expanding to the exit. So if we draw our first law around this, and we have power coming through, then we have our change in energy with respect to time is equal to Q minus W plus m dot H1 minus H2 plus V1 minus V2 over 2 squared. So this very long equation. And so in order to find what our power developed is, we need to make a number of simplifications. So we're going to assume steady state. We're going to assume no heat loss, or that this is at least negligible. We're going to assume any changes to velocity and potential energy of the incoming and exiting fluid are negligible. And that reduces this equation all the way down to W dot m dot is equal to H1 minus H2. And this H1 minus H2 is this H1 minus H2. So the important takeaway here is that this version of the equation can only be used if you can make these simplifications. If not, you would actually have a different equation for the top term here. Oh. And the same goes for the compressor. And then the last concept we need to know is cycle efficiency. So this one you'll have studied already quite a bit. And with this, what we're interested in is a ratio of what we want over what we pay for. Okay, so now we're just going to cover one more concept related specifically to this regeneration, and then we'll get into the question. So the Brayton cycle with regeneration looks quite similar. The only added part is this regenerator, and the purpose of this is to take any extra energy you still have in the turbine exhaust and recover it and add it into your incoming air. The more energy we add into our air going into the turbine, the more we're going to be able to extract. And so similarly to isentropic efficiency, the way we understand how this regenerator is operating is with our effectiveness, which is equal to the actual heat transfer versus the ideal heat transfer. Add the heat transfer there. And so we're just going to do a small proof here so that we understand where this equation comes from. So if you think about our regenerator, we have state 2 coming in and state X leaving. We have state Y exiting and state 4 coming in. And we have this heat exchange which happens from the exhaust air into the incoming air, or the air coming out of the compressor. And this we'll call Q heat exchanger. So we're going to draw our control volume, and I'm sure there's more than one approach to this, but I will draw my control volume in this way. And if we do our first law, we're going to say our steady state is equal to, and we're going to say no power. Q is being added, so we're going to add Q, our heat exchanger. We're going to add m dot, and this control volume only takes into account 2 and x, not 4 and y. So this is just h2 coming in minus hx leaving. So we will solve for our Q heat exchanger, and we'll actually do it per mass flow. This is equal to Hx minus H2. So this is going to be our actual operation, and if we just think for a second about what our ideal operation is, in our ideal operation, this kind of hot exhaust flow, or all the energy associated with this exhaust flow, we're going to actually transfer into X. Once X has the same amount of energy as 4, we're not going to be able to transfer any more energy through a heat exchanger, and so that would actually represent the max possible or the ideal heat exchange. And so for that to be true, it means that the energy associated with X, which we'll call Hx, would actually become equal to the energy associated with 4. And so if we therefore write out our effectiveness again, we're going to write this as our Q dot of our heat exchanger by our M dot divided by Q dot ideal by our M dot. That's going to be equal to Hx minus H2 divided by H4. This is now our ideal minus H2. And so with this equation, what we talked about above, we're now ready to solve the problem. Okay, so now we're actually ready to solve the problem. And before I solve this, I will just add the caveat that I do make mistakes. So if there is something you see on this video that doesn't quite sit right with you, definitely send me an email and let me know. But I will do my best to make this as accurate as possible. So the question asks, air enters a compressor of a regenerative air standard Brayton cycle with a volumetric flow rate of 60 meters cubed per second. So that's VA 60. 0.8 bar and 280 Kelvin. So the compressor pressure ratio is 20, and what that means is that our P2 by our P1 is 20. The maximum cycle temperature is 2100 Kelvin. And so this part of the question you need to think about, okay, what does this mean? Maximum cycle temperature. And if you look at the cycle, we're going to add, there's going to be heat added through the compression process. There's going to be added heat from the regenerator, added heat from the compressor, and then this is where we are going to be releasing a lot of our energy in order to produce our power. And so our maximum temperature is going to be referring to T3, 2100 Kelvin. So then for the compressor, the isentropic efficiency is 92%. And for the turbine, it's 95%. And the regenerator effectiveness, this is what we just learned, is 85%. So there's a couple of different ways you can approach this type of problem. The first one is to work through each one individually. So you start at A, and we know net power. We're trying to find net power developed, and so we would do first law around the compressor and the turbine, figure out which enthalpies we'll need to solve for that, and find our answer to A, and then move on. So as you do these questions more and more, you'll start to see that what always matters is the enthalpy at each state. So to find power across the compressor, of course, we're going to want to know how much energy is going in and how much energy is exiting, and we're going to use first law to find power across the compressor. And so one strategy that people, including me, like to do is to just go through each state and find enthalpy for each state, write that in a big list, and then go through A, B, C, D. And by the time you've found all the enthalpies, these questions will actually be quite easy. So that's how we're going to do it here. The only starting point we need to think about is we want to just give each question a very quick look and make sure we're going to need all the enthalpies. In an exam situation, or in a normal exam situation, you're going to be a little pressed for time. This year, we're going to see what the exam looks like. But we don't want to be finding enthalpies we don't need. And so we're just going to do this process. So for part A, we want to find net power developed. Net power is going to be power related to the compressor, power related to the turbine. So that means we're going to be interested in state 1 and 2 and state 3 and 4. So we'll find H1, H2, H3, and H4 for sure. And this is going to, we'll use that to find our work net. So state B is the rate of heat, or question B is the rate of heat addition from the combustor. So combustor, we're going to be interested in X and 3. So we'll look at Hx and H3. Finally, thermal efficiency of the cycle. So this was Qn. And remember that thermal efficiency is going to be equal to our net power divided by our Qn. I'll add some dots where I missed them. Okay, so there's nothing new as far as finding enthalpies with this question. And then how does the cycle efficiency change with increased effectiveness of the regenerator? So this one, it's a little bit hard to see exactly what we'll need. So we're gonna, when we come and solve that, we're gonna make sure that we got everything. But for now, what it looks like we need is H1, H2, H3, H4, and Hx. And so we're actually not going to bother finding Hy at this point. And again, if we find out later we do need to, we can always go back and find it, but this is just a method to save a little bit of time. Okay, so now we'll go through each state to find all the enthalpies we require. So starting with state 1, remember that for air, we're able to look up enthalpy with temperature only, not with pressure. And so what we're going to be looking for is H1, and we're also going to find PR1. This is because we're going to relate our actual state 2 to our isentropic state 2, and to find our isentropic state 2, we'll need PR2. So to find this, we will just go to the air tables. This will be table A22 in your book. We'll find the 280, and we'll read the H and the PR. So our H1 was 280.13 kilojoules per kilogram, and our PR1 is 1.0889. Okay, so to find state 2, we're actually first going to find our state 2s. So this is our ideal state 2s, and that's because we have this handy equation that we can use to find it. So we know that our pressure ratio of P2 over P1 was equal to 20. So this means that our PR2 is going to be 20 times our PR1, which will be equal to 21.78. So knowing that, we will find our H2S. So again, we'll go back to the air table, and we're looking for PR1 of 21.78, and we'll find that over here, and it's going to be somewhere in between these two numbers. So to find this one, we will interpolate, and once you interpolate, you would find an answer of 659.14. So next up, we'll be finding our actual state 2. So to find our actual state 2, we will use the efficiency of our compressor, which is H2S minus H1 over H2 minus H1. Now remember, previously we said that in order to use this, our kinetic energy and potential energy has to be negligible. and we have to be talking about steady state. So in this question, we're told volumetric flow rate, but we aren't told anything about the diameter of the inlet, so we're not going to be able to find velocity. So there's no information about this. There's no information about changes in height, and there's this. We have to assume steady state for this type of question because the non-steady state version is significantly more complex and beyond the scope of this course. So to me, all of these check out, so we're happy to use this version of the equation. So if we were to reorganize this, oh, missed a 1 there. So if we were to reorganize this, we're looking specifically for H2, and so this is equal to H1 plus H2S minus H1 over our compressor efficiency. And if we enter in everything there, we'd get 692.1 kilojoules per kilogram. And so if we do a quick sanity check here, we find that our actual state, or actually exit, has much more energy than our inlet, or than our ideal conditions. And what's essentially happening here is we're putting in power in order to cause this compression process to happen. And ideally, all we're trying to do is compress. That's the purpose of the compressor. And so if all it did is compress, it would increase the energy this much. Now, we do have some inefficiencies here, and the efficiency shows up by we're actually adding more energy to our fluid than we need to. Which means that our fluid will actually be, or air will actually be hotter coming out of the compressor than if it was ideal. And so we're taking some of the power we plan to use for compressing, and we actually turned it into heat, which was put directly into the fluid. And so that just gives you an idea of what the efficiency actually means. Okay, so the next thing we're going to do is we're going to try to find stage 3, and we're just going to scroll up to the picture. We're actually not going to find 3, we're going to find x first. And x, we're going to use the effectiveness equation we derived earlier. So we'll erase that, turn it into x. And what we said for effectiveness is our hx minus our h2 over our h4 minus our h2. So in this case, we know what effectiveness is. We don't know what our hx is. We know what our h2 is, and we don't know what our h4 is. And so there's kind of two unknowns here. So we're not actually able to solve this yet. And if we scroll up back to the picture, we're gonna just think for a second here about how we might get one of those extra things. So we're missing x, we're missing 4. And we can see that we're actually given T3. And so anytime we're given a temperature, we're going to be able to find energy right here. And we also know quite a bit about how to solve turbines. So we're actually going to jump right ahead to 3. We're going to use 3 to find 4, and then we're going to come all the way back and we're going to find x. Okay, so state 3, we know our temperature. This is equal to 2100 Kelvin. With the temperature, we can find our H3 and our PR3 using table A22. So reading from that table, we get 2377.4 kilojoules per kilogram and 2559. So similarly to the compressor, we're going to next find our state 4s. This will be our conditions of our exit of our turbine if we were operating isentropically. So to do that, we're going to take P3 by P4, and this is going to be equal to our reduced pressure ratio. That is a PR3 and PR4. And this pressure ratio is equal to 20. So we're going to be using the same pressure ratio that we had across the compressor. We'll always be able to do this because it's assumed that the pressure drop across the heat exchanger is 0, and it's also assumed that the pressure of the inlet and the exit are the same. And that's actually quite a good assumption, knowing how the real system operates in that schematic shown above, because both the inlet and the exit are taking and venting out to atmosphere. So unless there's something in the question that says you have to assume pressure drop required a heat exchanger, or it explicitly says that the inlet and exit conditions are different, you can always use the same pressure ratio. So reorganizing this, we get PR4 is equal to PR3 over 20, which works out to 127.95. Okay. And then using that pressure ratio, you'll go back to table A22 and you'll find H4S. This is equal to 1078.98 kilojoules per kilogram. So now we'll look for our actual state 4, which we'll find using our turbine efficiency. So turbine efficiency is H3 minus H4 over H3 minus H4S. So H4 will be equal to our efficiency of our turbine, or rather H3 minus the efficiency of our turbine times H3 minus H4S. Solving for that, we'll find 1143.9 kilojoules per kilogram. And once again, we can do a little sanity check. So the purpose of a turbine is to take all of the energy that's held before the turbine in state 3 and turn it into power. And so if our turbine was working as well as possible, it would turn as much of it as it could into power. And that's what this state 4S represents. This is thermodynamically the maximum amount of energy, the difference between this and this, it could turn into power. In reality, it did not turn all of it into power, and so we're left with a little bit more energy in our final state than we're necessarily limited to thermodynamically. Okay, so now that we have state 4, we're actually going to go back up to state X, which is the one that we couldn't solve before, but now we can because we have state 4. And we'll find that our Hx is equal to the effectiveness of our heat exchanger times H4 minus H2, and then we're going to add H2 onto it. So this will give us an Hx of 1076.13 kilojoules per kilogram. Okay. So that was the end of the first part, where we're just trying to find all of the H's, and so I'm just going to write out a quick summary so that way we can move on to the next part of the question. So now that we've solved for all the enthalpies, we can go ahead and start solving our problems. So A is asking for net power. Net power is going to be the power produced by the turbine minus the power used by the compressor. So the turbine power, we have state 3 going into it and state 4 exiting. And we're producing our turbine power. So when we write out first law for this control volume, we get change in energy with respect to time is equal to Q minus turbine power. Now, this is minus because our work is, or our power is leaving our turbine, plus m dot h3 minus h4, and then we also have our change in kinetic energy term and our change in potential energy term. Okay, so as usual, what we're going to do is we're going to neglect these, and we're going to neglect them because no information is given about them. So if you are given information about, let's say, velocity, or if you're told what the diameter is of an inlet, that's often a hint that you're going to be able to solve for velocity. You will want to include this. This is a little bit less common in these types of questions, but it's not inconceivable that you'd be asked or told something about potential energy. Though in this question, we're not told anything about them, so we just have to assume that the changes are negligible. Same with our heat loss. So it is possible that we're losing heat, but we're not told anything about it, and it's probably that power we're losing from the heat is probably quite small compared to what we're generating. So we just assume that in the grand scheme of things, we could neglect this. And we're also going to assume steady state, so that's going to go to 0. So this gives us our turbine power is equal to m dot h3 minus h4. And the nice thing is we have h3 and we have h4, but we will need to find m dot. So our compressor power, this is with states 1 going in and 2 exiting. I'm going to be a little bit lazier about my first law here, so we're steady state, and this time we're actually putting our power in to the compressor, and so we are going to add our compressor power. So previously we subtracted it because we were removing it, now we're adding it, and so we're adding it here. This, we're going to make the same assumptions about potential energy and about kinetic energy, and so this will simply be 1 minus 2, which simplifies down. So we're going to flip the order of this just to eat up the negative that would have appeared here if we hadn't have done that. Okay, so like I mentioned, we have all of the h's, but we do still need to find the m dot. All we're given in the question is volumetric flow rate, but we do know that our mass flow rate is equal to our volumetric flow rate divided by our specific volume, and we also know that our pressure and temperature are all related to our specific volume through the ideal gas law, which is PV equals RT. And with this specific way I've written it out, this R is R specific, which is equal to R bar, the universal gas constant, over the molar mass, which for air works out to be 8.314 over 28.97. This is kilojoules per kilomole Kelvin, and this is kilograms per kilomole. Oh, my mistake. Okay. So this means our specific volume is RT over P, which is 8.314. And remember, we're specifically looking for our specific volume at 1 because that's where we know our volumetric flow rate. So our volumetric flow rate won't be conserved throughout the whole system. So we can't just use this volumetric flow rate at any state. We have to use the volumetric flow rate or the state information about to find our specific volume at our state 1 so that we can find the mass flow rate at that specific spot. And then the mass flow rate is the same throughout the entire system. So we're going to write this out again. This whole thing is in kilojoules per kilogram Kelvin. The temperature at our state 1, which is 280 Kelvin. The pressure, which is 0.8 bars, which works out to 80 kilopascals. And we get a specific volume of 1 meters cubed per kilogram. So that's quite nice. So that means that our mass flow rate, which is true everywhere, is equal to our volumetric flow rate at state 1 divided by our specific volume at state 1. And since our mass flow rate is equal to 60 meters cubed per second, our volumetric flow rate was 60 meters cubed per second. Our mass flow rate will simply be 60 kilograms per second. Okay, this means our net work is going to be equal to that 60 kilograms per second divided by our H4 minus H5. This was our turbine power, and then minus our H2 minus H1, and this was our compressor power required. So when we plug in all the values we found for this, we'll get 49.292 megawatts. Okay, so for part B, what we're interested in now is our Qin. So we're trying to find, and so if we just draw our combustor, we have our Qin. Into our combustor we have our state X, and exiting our combustor we have our state H, or our state 3. So our quick first law, and again I'll do kind of our lazy first law here. So we have 0 is equal to, okay, we know there's no power produced by a heat exchanger. We have Qin. The fact that it's in means we should add it. So Qin plus m dot. Once again, we know we have no change in potential energy, no change in kinetic energy. So this is going to be Hx minus H3. Making our Qin equal to m dot H3 minus Hx. So we know m dot, we just calculated that in the last question, 60 kilograms per second, and we know H3 and Hx already, so this means that our final answer can be calculated to be 78.076 megawatts. Part C asks for our thermal efficiency, which is again what we pay for, that net power, or sorry, what we're trying to achieve, which is that net power divided by what we pay for. And of course what we pay for is more than what we get, and in this case we have just calculated this, so we're looking at 78.076 divided by 49.292, which is equal to 0.63%. And finally, question D asks for how does the efficiency of the cycle change? So what happens to efficiency if we increase effectiveness? And what would intuitively be true is that if we increase effectiveness, our efficiency would also increase, because why would we have this if it being not effective would increase efficiency? But that said, we'll actually show you why. So in this question, H3, or rather temperature 3, was fixed. So this H is not going to change. So the regenerator, actually I'm going to show you on the main picture, all the way back up here. So we knew that this T3 was going to stay at 2100. This is something that defines this question. And so if we increased effectiveness, what we would actually get is a increased amount of energy at point X. And if we have an increased amount of point of energy at X, we wouldn't need as much Q in order to be producing the same amount of power that we're currently producing. So we'll go all the way back down. So that said, with increased effectiveness, this means we need less Q in to get the same power. So if we have our power stay the same and we have our Q in decreasing, it means that our overall efficiency increases. So that's the answer to part D.